So good morning to all. So today we will be discussing about Lagrangian equation, and we'll also address few problem regarding that as well. Okay. So we'll start with Lagrangian equation representation. In this case, now we know familiar with the Lagrangian equation earlier also. Okay. So in the absence of a constraint, we know that in the absence of constraint, when you say that in the absence of constraint, the Lagrangian equation, as we know, it is actually represent the Lagrangian equation of motion. When you represent Lagrangian equation of motion, so we do represent it like this: d by d I dou L q I dot, okay, minus dou L by, so it is dt, right? D by dt, okay, yeah. Dou L by dou qi, which is equal to 0. So this is how we do represent this one, where this is di. Okay. So in the presence of a constraint where psi k equal to 0, then we say that this representation, so in the presence of a constraint where psi k is equal to 0, okay, by Hamiltonian principle, so we know that by Hamiltonian principle, Hamilton's principle, we can say that del equal to integral L qi dot comma t plus sigma k lambda k. When you represent sigma k of t, it is actually with respect to t, and you have psi k of qi comma t dt will be the representation corresponding to that, which is equal to 0. So that is the Hamiltonian principle when you say that. And when you say that the constraint Lagrangian equation of motion corresponding to this one, when you say the constraint Lagrangian equation of motion, okay, so now when you say the constraint Lagrangian equation of motion, so it becomes, we will be having the value that is d by dt. I think this is d by dt, right? Then so d by dt of dou L by dou qi dot minus dou L by dou qi, which is equal to, we know that it is sigma k aik lambda k is the corresponding equation we have. So here when you have a constraint, so this equation of motion will not be 0, instead it will be a non-zero quantity associated with that. And now we say that psi k is a constraint that we have represented here. Psi k, in this case we can simply represent that psi k is a function of what? It is a function of q and t, that is already represented in the above equation also. Okay, so it is independent of the generalized velocity. Okay, what is the which is independent of generalized velocity. What is generalized velocity? Generalized velocity is the representation that we already said, that is about qi dot, which is independent on the this constraint is dependent only on the position and the time. Okay, it is independent of the generalized worded qi dot. Okay, so in this case, when you say the coefficient of aik is given by, so when you say in that representation the coefficient aik, so it is a coefficient which will be equal to what? Which will be equal to dou psi k divided by, which is equivalent to dou qi dot. So that is a uh, representation that we will be getting corresponding to here. Now what I say is that what is this aik lambda k means, where aik lambda k is actually the force of the kth component. Okay, it is the force of the kth constraint. Okay, constraint in the qi direction. That's what I would like to say. Okay, so it's a force actually representing, and exactly same like if you take so it is the same representation like if you take dou, for example, in terms of if I represent dou ik lambda k, which is equivalent to if you are taking dou v by dou qi. Okay, so which is equivalent to that one, because we know that f is equal to minus del u, or this representation, right? And similarly we can represent like that as well. Okay, so which is exactly same as minus dou v by dou q in our actual representation. Why it is dou v by dou q, where it is actually representing the velocity with respect to qi. Okay, that means the acceleration corresponding to that will be getting corresponding to that. Okay, so now we'll put this Lagrangian constraint Lagrangian equation in a few examples. So first example I'll be taking here is that I'll be taking a sliding log case. Okay, where a sliding log means we have a piece of wood or something. Okay, so which we have taken as we have a sliding of a log. Okay, so we have, okay, so we are actually a sliding of a log. That means a particle is sliding on a cylindrical surface here in this case. Okay, so let's take example. We have a particle. Okay, so a particle is sliding on a cylindrical surface. So what our objective is that, so we have to find, our objective is to find the critical angle corresponding to critical angle theta c at which the particle flies off from the surface. So that is our objective for this, considering in this particular case. Okay, so that means we have a, like if you represent, so we have a sliding log over here. So we have something like a piece of something, a particle or something, so which is actually sliding on this surface. Okay, and when you examine, so we have to say that at a critical angle theta, this is falling down. Okay, it is actually falling down. So this is the distance I can represent as r. So a particle, so which I do represent with smaller particle instead of a log. Okay, so considering this particular problem, what do we examine is that we just consider a simple log that we are placing, that like if you are placing a wood or something, no, so we just simply say that we are actually putting a, a simple particle which is actually falling down on that particular critical angle. And what is the critical angle? So critical angle is the angle at which the radial force of constraint goes to 0. So when you consider in this particular situation, the importance of critical angle is that the critical angle is the angle at which the radial force of constraint goes to 0. So it is actually goes to 0 in this situation, that is a critical angle. And now in this particular problem, if I say the Lagrangian corresponding to that, we know Lagrangian is what? It is actually L equal to T minus V, and which will be equal to this particular case, that is half mr dot square, okay, plus r square theta square is the corresponding, minus we'll have the radial force, that is mgr cos theta corresponding to this as well. Okay, and when you consider the equation of constraint here, so we can say that, and we'll have one equation of constraint also associated with that equation of constraint, so that I can say that this is equal to what? Psi equal to r minus l, which is equal to 0. Okay. Okay, so when you say that this representation, okay, so in this case, when you evaluate the value corresponding to that, that is mr dot, okay, minus mr theta dot square plus mg cos theta, okay, mg cos theta equal to, we say that it is lambda 1 of theta, okay. And now if you further evaluate, this is not mr dot, sorry, this will be mr double dot, okay, this is mr double dot corresponding to that. And now we say that that is equal to what? Mr square theta double dot will be there when you evaluate along with respect to theta, and this will be equal to mr r dot theta dot minus mgr sin theta when you evaluate with respect to theta. Okay, so this will be equal to 0 when you differentiating this one. So in which when you consider this case, the constant of force lambda 1 theta is a function of the angle theta, so that you can see that. So the constant, the constraint force, not constant force, the constraint force we represent here, it is lambda 1 of theta, is actually what it is, depends on the angle. So it is depends on theta basically. So where lambda 1 is what? Lambda 1 is the radial force. It is exerted by what? Exerted by the cylinder. So lambda 1 is the radial force exerted by the cylinder on the particle. So lambda 1 is that basically. Okay. So now we say that our, since if you consider that since r equal to L, okay, r equal to L, then r dot equal to what? R dot equal to 0. Okay, so that means when you say that the equation, if you substitute r equal to L, then you will have ml theta dot square plus mg cos theta, mg cos theta equal to, we will be getting as lambda 1 of theta. Okay, and now you further, if you evaluate, you will be having ml theta dot minus mg sin theta as the second equation. You will be getting like this. Okay, so this is our first equation, and this is the second equation, and first equation becomes like this, and second equation becomes like this. Okay, so this is how it transform into that case. And now if you differentiate with respect to time, now if you differentiate uh, equation with respect to time, okay, now the df of theta divided by dt, so which has to get what? It is a function of df of theta divided by d theta into theta dot will be the corresponding representation we will be getting from here. Okay, and when you say that, you will be having the corresponding solution corresponding to that. This will be equal to 2 ml theta dot minus mg sin theta which is equal to d lambda 1 of theta divided by d theta. Okay, so now if you want to eliminate the value of theta double dot in the equation by using second equation, actually you can replace that. So then the integer, the integral becomes, in that case we will be getting lambda 1 of theta will be equal to, we will get finally as 3 mg cos theta plus c. Okay, now if I say that lambda 1 equal to 0, okay, that is theta equal to 0, if I consider, then I can say that lambda 1 of 0, which is equal to what, mg cos theta, if substitute, you will be getting 3 mg corresponding to, you will be getting, okay, yeah, you will be getting 3 mg corresponding to that. And you will be getting, while substituting this one, you will be getting as c equal to what, c equal to, you will be getting as minus 2 mg as the value corresponding to this one. Okay, so the particle m will stay on the surface as long as the force of constraint is non-negative. Okay, so that means as long as the surface has to push outward the particle, the lambda 1 of theta should be equal to what, which should be equal to, in order to pull out that one, so we should say that the lambda 1 of theta, will be equal to what, which is equal, lambda 1 of theta equal to, we'll get a 3 mg cos theta minus, we put the value of mg, so that is equal to 3 mg, so minus 2 mg should be greater than or equal to 0. Okay, as long as the surface has to push outward the particle, to push outward the particle, so lambda 1 of theta should be this value. So the critical angles lies between where, so the critical angle will be at a lambda theta c equal to 0. Okay, so this is the position where you can see the associated critical angle. Okay, and the force constraint going to 0 at that situation. From uh, at this position we say that the force constraint will go 0. Okay, force constraint will tends to 0 as well, and we get that cos theta c equal to what, it will be 2 by 3, or rather we case the theta critical angle will be 48 degree 11 minutes, like you will be getting the corresponding value. Okay, so at this angle, one can say that our particle, so far our discussing, our particle will fly off. Okay, it will fly off from the position. Okay, so this is simply a simple execution of the above representation. So what we have done is that in this representation we actually has been executed. So mainly we address it once you get the value corresponding to that Lagrangian. Okay, so here we have got the Lagrangian value. Now if you want to put the divide by dt of dou L by dou L by dou qi minus dou L by qi dot will be there, dou L by dou qi sigma ak lambda ik, right? Okay, this is the representation we have. Now here we have two value, because theta and t has been theta and r are the two value changing parameter. So while you do the differentiation, there will be two way you have to differentiate, dou L by dou r and dou L by theta, and both way if you do, you will be getting two equation corresponding to, that is equation number 1 and 2. Okay, so like where we got the value, and finally we got the critical angle corresponding to this as well. Now we'll take an example of simple pendulum here. So that is the second example we'll be taking of here. So example 2. Okay, so we know that as simple pendulum case, it is very familiar with the case of simple pendulum. Okay, we have a pendulum. Okay, assume that this is at the center. Okay, so my drawing won't be good. Okay, so this will be the theta between that, and the ball is actually moving on to and fro. Okay, so consider a simple pendulum where the mass, which having a mass m. Okay, constrained by the wire length. So here the constraint is actually the length of the wire, that is we are actually taking as a constraint to. So this constraint in L to swing in an arc. So it has to swing like an arc. So the constraint is that, and we here psi 1 is equal to r minus L, that is equal to 0. So in the absence of constraint, we can represent this one. Okay, and there are two generalized coordinate in this representation also. We have r and theta, and we have two components also here. 2r and theta are the two generalized coordinate in this representation also. Okay, so when you evaluate that, we know that the Lagrangian for simple pendulum, that is equal to what? It is equal to t minus v. So that is equal to, will be getting us what? It is half mr square, half mr dot square plus r square theta dot square. Okay, plus we will have mg r cos theta is the corresponding Lagrangian. And here what we take is that if you're taking the potential energy, in this case potential energy, if you take to be 0. Okay, so where the, when it will be 0, so in that case where the pendulum will be what? So in that time pendulum will be horizontal. Okay, horizontal. So at that situation we can say that theta will be equal to what? It will be equal to pi by 2. Okay, so by that equation, so we can say that we can simply address that problem if you have the potential energy, if you take it as 0. And we know that the Lagrangian equation here we have to take it as d by dt of what? Dou L by dou Q I dot, that is the equation that is already we have learned. And now we know that that is dou L by dou Q I, which is equal to sigma k aik lambda k. So this is a representation corresponding to that. Okay, so now here also, like earlier case, here also we have to do this differentiation with respect to d by dt with respect to since we have two coordinates over here, so we have to take dou L by dou r minus dou L r dot. Okay, r dot, and we will also have to take dou L by dou r, which is equal to lambda L. Okay, and we also say that d by dt of the second generalized coordinate we have to take with respect to theta dot minus dou L by dou theta, which is equal to 0. Okay, and now if you say that here uh, ar1 the will be equal to 1, and a theta 1, that is equal to 1. So acceleration due to these two value can either you can do represent like this. And now we say that the d by dt here, d by dt we have to evaluate with respect to mr dot minus mr theta dot square okay, minus mg cos theta will be there. Okay, which is equal to lambda 1, that's the first representation. And the second one, we have to differentiate d by dt mr square theta dot plus mgr sine theta, like the same earlier, like we will be getting. Now if you substituting the equation constant here, Okay, equation of constraint here. Okay, now if you substitute equation of constraint, that is r minus L equal to 0, that means what? R equal to L. Okay, and R dot we know that is equal to 0. Okay, now in that case we'll have ml theta dot square plus mg cos theta. Okay, which is equal to what? Which is equal to minus lambda 1, and we'll have the second equation, we'll have ml theta double dot, okay, plus mgl sin theta, which is equal to 0. These are the two equations we'll get corresponding to here. Okay, so what is this ml theta dot? That is, we know that it is actually the tension. It is a tension in the wire or that simple pendulum wire or something. Okay, so which in terms of what? In terms of theta and theta dot will be representing, and this is now, we know that it is a simple harmonic motion. This is actually representing a simple harmonic motion associated with that. Okay, okay, so if the amplitude is very small, if the amplitude is very small, okay, so that is a representation we'll have either on the both side. Okay, sorry, no, this one, this one. Okay, okay, so here the Lagrangian multiplier will be a function of what? So the Lagrangian multiplier lambda, or rather it will be, when you say that, the Lagrangian multiplier in this case will be what? It will be a function it will be a function of time and theta over here. Okay, so that's what only we have to share about simple pendulum case. Also, if you want to know that details, that also you can execute, but we are not going much details about that. Next example, we are taking the consideration of, by taking this Lagrangian representative equation, how do we evaluate the Schrodinger wave equation? Okay, Schrodinger wave equation representation. So, in Schrodinger wave equation, we are actually finding, we have to find the Euler equation for a quantum mechanical problem. That is, firstly we need to find the Euler equation for a quantum mechanical problem. So for that we have delta over here, so that we have to take on integral. So we have given with the wave function psi x y z. Okay, so on a Hamiltonian we will be evaluating with respect to psi x y z, psi star h, psi star x y z, h psi x y z. Now we have to evaluate our volume dxy dy by dz, that's equal to 0. So this is how our Hamilton's principle will look like for a wave function corresponding to case. Okay, so with the normalization constraint, if you consider with the consideration of a normalization constraint, okay, so we know that the integral psi star psi dx dy dz, that's equal to what? It should be equal to 1. So it is a statement of the energy of the system is stationary. Okay, so this again, this statement is what? It is the energy of a system. Energy of a system is stationary. So that is the statement that you can see from this one. And where h, we already know h is what? H is the quantum mechanical Hamiltonian for a particle of mass m. Okay, where h, we already know it is a quantum mechanical Hamiltonian corresponding to Hamiltonian for a particle with mass m. Okay, And now also we know that where h is a differential operator, so h can I can simply write it as minus h cross by 2m, okay, 2m del square. So it is an operator into v x y z, where we consider within a potential case. And the above mentioned constraint is a bound state constraint, okay. So here we have a bound state constraint, okay. So it is within a box we have to consider. So the constraint is bound state constraint, and psi is the wave function. It is a dependent variable. That is already we said that psi is a wave function corresponding to that, because psi x y z, okay, is a dependent. So which is depending on x y z, so it's a dependent wave function. And we also know that psi star is actually representing the complex conjugate of that particular wave function, okay, complex conjugate of that particular wave function, okay, which is located in the second dependent variable. That is also we have seen. And in the equation we have seen that delta should be equal to, by Hamiltonian principle, so we have seen that equation psi star xyz, okay, psi star xyz h psi xyz, when you represent, so that is equal to dxy di dz should be equal to 0. So that is the energy is a stationary value, that is we have said also addressed, okay. So the which contains a second derivative which can be convert the first derivation. When you do this derivation by taking delta over this particular function, so you will be having two cases, that is so when you evaluate, so we have to take psi star dou square psi by dou x square dx will be equal to psi star dou psi by dou x minus integral dou psi star by with respect to dou x we have to evaluate, and dou psi by dou x dx will be there, okay. So here we have taken only one along x direction only. Similarly you have to take on y direction and z direction also. So considering a periodic boundary condition here, so if you consider a periodic boundary condition over here, so in that case when you integrate this particular function with integration by parts, then you will be having delta, okay. Then you have to give the value corresponding to the del psi star, okay, del psi plus b psi star into psi, okay, like you have to give when you have given the operator dx dy dz, okay, which is equal to 0. So here we have consider, so the function, for example, if I do represent this particular function as a g over here, where g equal to, so let me just say that is a function of g. So where g equal to what? G equal to h cross by 2m del psi star del psi plus del psi star minus lambda psi star psi will be the corresponding value, okay. Now if I say, if I do expand this terminology, so what I be supposed to get is that it will be minus h cross by 2m. So we'll get that psi x star psi x will be there. On the other hand, we'll have with respect to y, psi star psi y will be there, plus we'll have psi z star psi z will be there, and plus we'll have v psi star v psi minus lambda psi star. This is actually v, okay, v psi star, okay. v psi star lambda psi star psi will be there. Okay, so that is a g value over here. So here g you can simply represent like that as a function of case. Okay, now again using our subscription to the x, if you denote dou by dou x equal to y, for y I you can also give that psi y. So if you do so, okay, so when you say that dou g by dou y, dou g by dou y will be equal to, so in terms of yi, dou g by dou y minus, simply I can say that there is sigma j dou by dou xj dou g by dou yi by dou xj, which is equal to 0 we have to utilize. Okay, so what we are doing is that we are taking the subscript x2 to denote dou by dou x. For yi it is actually psi, the corresponding psi value psi star, and is actually representing the value of psi star over here. So this equation, what it becomes is that, so the above equation becomes in that fashion, that is dou g by dou psi star. Okay, dou g by dou psi star minus dou by dou x. Okay, dou g by dou psi x star, okay, minus dou by dou y dou g by dou psi y star minus dou by dou z dou g by dou psi z star, which is equal to 0. Here we have given with yi equal to, in this particular equation we have substituted yi equal to psi star. Okay, so that is that we have given, and we know that wherever you have psi x or something, so it is actually representing dou psi by dou x. Similarly psi y means it is actually representing what? It is representing the value corresponding to, we are taking the differentiation like this. And finally if you put like this in the equation, so what you will be supposed to get is that the equation will be yielding that v psi minus lambda psi will minus h cross square by 2m will get us psi xx plus psi yy plus psi zz, which is equal to 0. Okay, so this above representation will yielding this formula that is corresponding to that, or rather I can also represent this minus h cross by 2m, okay, del square psi. So it is a this psi xx means it is actually second order derivative, right? So it is del square psi plus v psi is equal to what? Is equal to lambda psi. Okay, so this is actually what? It is a Schrodinger equation. Okay, so it is a Schrodinger equation with a constraint. Okay, so it is a constraint case. Okay, now we can actually compare this above representation with the Hamiltonian, because Hamiltonian is what? It is h square by 2m del square, okay, plus v of xyz. Okay, so you can now compare with the above representation. We are actually getting the same representation here as well, for where this representation is what? It is actually h psi. Okay, h psi. So this I can simply write is h psi equal to lambda psi. Okay, so this entire notation we can simply write it over here. So where lambda is the physically the energy of a quantum mechanical system. Okay, so what you are supposed to get is what? So here we are getting lambda, it is the energy eigenvalue corresponding to that, because we are operating on a Hamiltonian, operating on a wave function psi, and the corresponding value will be what? It is the energy eigenvalue. So I can simply say that lambda is physically meaning what? It is physical means that it is the energy of the quantum mechanical system. Okay, so this is a variational so what we have done so far is it is the variational approach. So this is a variational approach towards the particular equation. Okay, right, towards this equation. So similar approach has been, we are also approaching for simple pendulum case and the sliding of a particular log case. Okay, so that's what we have done here today. So we have discussed about Lagrangian equation, and we have Lagrangian equation with constraint we have seen, and from that Lagrangian equation with constraint we have taken 3 examples of simple pendulum, and we have taken the case of Schrodinger wave equation, and further we have also taken the sliding of a log case as an example of Lagrangian equation with a constraint. So then we have executed a variational approach for different kind of these problems. So that's what we have done here, and on the next class we will be discussing about the Rayleigh Ritz problems, and those formulas also will be discussing on the next class. Okay, thank you.